Okay, well, we're very happy to have Tom Hartman from Cornell University. Tom has done very beautiful work ranging from ADS CFT to null energy CFTs, null energy conditions, and today is going to tell us about replica wormholes and the information paradox.
All right, thanks a lot for having me. This will be fun. So in this talk, what I'm going to do is I'm going to give a broad overview of developments over the last 2 years or so on the information paradox. And I'm going to start with some background on the page curve and the statement of the paradox. So this is a Penrose diagram for an evaporating black hole. There's a star, that's back here. You can see my mouse, right?
Yeah. Yes.
Okay, I'm never sure. There's a star, the star collapses, the black hole forms. This is the event horizon. And we live out here in the future infinity outside the black hole, and we imagine collecting the Hawking radiation out here. So the Hawking radiation is produced with one Hawking, roughly speaking, you can think of this as pair production across the horizon, with Hawking particles created on the outside and some interior partners on the inside, because the quantum state on a full slice like this long green one here, the quantum state on a slice like this is pure. So if we have some thermal radiation on the outside of the black hole, then it must be actually secretly entangled with something. And that's really the point that I want to make on this slide, is that Hawking radiation is a process of entanglement production between the black hole interior and the radiation. And that way of thinking about it is going to be key here. So to discuss the paradox and the page curve, we're going to consider the fine-grained, and I should have said, please jump in and interrupt me with questions and we can discuss things. A lot of these things maybe you've heard, but this is a chance to stop me. Okay, so good. Consider the fine-grained or von Neumann entropy of the radiation. So that is, we pick a region, the radiation region out here far away from the black hole where we collect the Hawking radiation. And that's our region rad. It has a density matrix rho sub r, which is approximately thermal according to Hawking. And we calculate its von Neumann entropy, which is the fine-grained entropy minus trace of rho log rho. It's important in this discussion that we're talking about a fine-grained entropy. This is really the entropy that you still have left over when you know the exact quantum state of the radiation, the density matrix rho sub r, as opposed to a coarse-grained entropy that we would normally talk about in thermodynamics. The fine-grained entropy in particular is 0 if you're in a pure state. So the page curve is a plot for what the entropy of Hawking radiation should look like. Here's Hawking's calculation. So Hawking's calculation says that after the black hole forms, so it forms right around here at the beginning on the left, then the black hole should evaporate. It evaporates into Hawking radiation. The Hawking radiation is thermal. So the entropy of the radiation goes up, up, up until the black hole is done evaporating. That's here. And then the radiation is still thermal, and the entropy just saturates and stays there forever. So this is one way of stating the paradox, is that when the black hole is gone, the radiation should be in a pure state and therefore should have 0 fine-grained entropy, but apparently it does not. Apparently it has some large thermal sized entropy. We can make that a little sharper by comparing that to the area of the black hole, because we think that if quantum gravity is a unitary theory of quantum mechanics, that black holes should obey the ordinary laws of quantum mechanics, and in particular, they should really just be ordinary quantum systems. We also think that the entropy of a black hole is given by its area over 4. And if you entangle, so what this does is this places an upper bound on how much entropy you can have in the Hawking radiation. And in particular, you have a paradox, an information paradox, or this is some version, maybe we could call it the entropy paradox. As soon as these two lines cross, you have a paradox. Because I said that the entropy in the radiation comes from entanglement between the radiation and the black hole. But when you entangle with something, you can only create, by entangling, you can only create as much entropy as the amount of stuff that you're entangling with. Okay, so this area over 4 is an upper bound on how much entropy you can make by entangling with the black hole. And when we get to this part of the second half, roughly, of the evaporation process, the black hole is small. It's not big enough to create all this entropy by entanglement. So really, the paradox starts here when the two lines cross. So Don Page looked at this from the point of view of just general properties of unitary quantum systems and predicted that since quantum gravity is pretty complicated and black holes are pretty complicated, that's really the main input that goes into his argument, predicted that the actual plot of the fine-grained entropy should look like the dotted line. So it should go up with Hawking's calculation at the beginning, but right here when the paradox appears, the Page curve should turn over, and as we collect more and more Hawking radiation, the fine-grained entropy should actually go down. So what's happening in the second half of the process here is that when we receive so say we're somewhere here, if we receive another Hawking particle, it's entangled with the ones we already collected. So receiving that new particle actually makes the fine-grained entropy go down, because if you have access to both of the entangled particles, they're now together in a pure state, and the fine-grained entropy is smaller. So that's what it should look like in a unitary theory, and the paradox is that Hawking's calculation gives something different. We should be careful about the word paradox, so let me discuss that for a minute. So we're working in the low energy effective theory. Hawking is working in the low energy effective theory. So when we say that the Hawking radiation is thermal, what we really mean is something more like this, that there's a thermal leading order calculation, the thermal component. There can be corrections to this. There are perturbative corrections that in principle we could calculate if we knew what all the particles are that it can radiate to, and we knew how to calculate all the loops. And in principle, we could calculate these using quantum field theory. Then potentially there are non-perturbative corrections which are suppressed by quantum gravity effects that are e to the minus s, where s here is the black hole entropy. Now, there's sort of a loophole in Hawking's argument and in discussions of this, which is that e to the minus s corrections to the matrix elements of the density matrix of the radiation are big enough to change the entropy at leading order, and in particular to change it from looking non-unitary to looking unitary. Because when you calculate the entropy of the radiation, you're doing this trace, and so you're doing a sum of e to the s term. In principle, you're supposed to do a sum of e to the s terms, and if each of those terms has an e to the minus s correction, then you can get large effects here. Okay, so if we really keep track of what's reliable and we allow any old non-perturbative corrections that we want and just say, well, we don't know how to calculate them, then there is this sort of loophole in the logic that this is a paradox, and we're going to end up sort of exploiting that loophole. So why do we call it a paradox? Well, two reasons. One is that the local or perturbative corrections that you get in quantum field theory, these terms, don't help. In fact, you can prove that it's impossible to fix the problem with any kind of local physics. The second reason, well, so that means if there's a fix, it has to be in these e to the minus s terms. But that's not really a fix, because there's no known mechanism for producing these terms and allowing the information to escape. So that's why it's a paradox. To summarize briefly the new developments, there are e to the minus s corrections to the gravitational path integral that produce large corrections to the entropy. This new calculation gives a small entropy that's consistent with unitary evaporation. The ideas that go into this came from ADS-CFT, but nothing in this calculation really relies on that. It's not really using any of the high energy features of string theory or anything about ADS. A caveat that I should mention right from the start is that we're going to use path integral methods, and these path integral methods sidestep some of the difficult aspects of the paradox. So this is going to give us a calculation of the entropy, but it's not going to solve the entire puzzle. It's just going to help us understand one piece of it, and I'll come back to that in the remarks at the end.
Tom, can I ask a question?
Sure.
It would seem like that these small corrections, e to the minus s, are only sort of big enough at the beginning of the page curve, or I mean, it looks like from the page curve that after you're past the page time, you need very big corrections. So can you just comment on that, or maybe you'll comment on it later?
Well, what I had in mind here is that we collect all the radiation. We have some density matrix rho sub r after collecting all the radiation, and that then we're talking about the tiny corrections in that's now a fixed density matrix. And somewhere along the way, somewhere during the evaporation, we need to have accrued some e to the minus s corrections to those. But you're absolutely right that late in the evaporation, the change in the entropy has to be huge. It has to be leading order. And we're going to produce an effect like that.
Okay, thanks.
Okay, any other questions at this point? Okay, here's some references. Let me just point you to a review article that we wrote at sort of a conceptual level that I'm sort of following in this talk. As I mentioned, a lot of the ideas here came from holographic entanglement entropy. I'm not going to go through that story. I'm just going to jump to the applications of these ideas to the information paradox. So this started with the proposal of two papers in 2019, one by Pennington, the other one by Olmeri, Engelhardt, Marloff, and Maxfield. And they proposed an effect that's now called islands, or the island effect. So let me first tell you what this is. This is a conjecture this is a conjecture for the entropy of Hawking radiation. And they made this conjecture motivated by ADS-CFT. And it was then later derived from the gravitational path integral. So that's the logic here, and I'm going to present it in that way. That first, I'm going to give you the conjecture as it was made in these two papers, and then we're going to derive it from the path integral. So here's the island conjecture. Again, this is our picture of the evaporating black hole. The red region here is the radiation. And our goal is to calculate the von Neumann entropy of this region. So they proposed a formula for this. Here's the formula. Well, in words, what you're supposed to do is first you're supposed to put in by hand an island in the black hole interior. That's the blue region. That island is going to be determined dynamically. You don't pick where it is. You allow it to be anywhere, and then it's going to be picked out by this formula. So here's what you do. You calculate this quantity in brackets, which is a generalized entropy. It's a sum of an area term. The area of the island over 4 is the first term. That's roughly the black hole entropy, because this island is roughly going to end up being the black hole. But a priori, it's just any old region. So you have an area term, and then you have a quantum field theory term. But the quantum field theory term, so the quantum field theory term, this just means something you would calculate by the ordinary methods of quantum field theory in curved space. This QFT term is funny because it's for the joint region of the radiation union the island. So you calculate this generalized entropy, then you extremize over the choice of island, I. If you find more than one extremum, you then minimize over the various choices of extrema. And that's the formula. Something I want to emphasize about this formula is that if the Hawking radiation is out here in rad and the island covers the black hole, then the Hawking radiation, the entropy of the ordinary Hawking entropy does not contribute to this formula. Because if there's a particle out in rad, a Hawking particle out in rad, then it has an entangled partner inside the black hole. And in this entanglement term, this is the fine-grained entropy of the joint of the pair of particles. But the pair of particles together is pure, so it does not contribute to that fine-grained entropy. Okay, so so the important point is that Hawking radiation doesn't really contribute much to this term. What you find, so you can do this calculation, do the extremization, and what you find is that at late times, the island is, there is an extremum, and the island is basically the full inside of the black hole interior. As I explained, that means the Hawking radiation doesn't contribute. And the second term actually is small. There's nothing to contribute to it. So Hawking radiation does not contribute to the second term. This formula for the radiation entropy then reduces to 1/4 of the area of the black hole horizon. And that goes to 0 as the black hole evaporates. So if this formula is correct, then it is consistent with unitary black hole evaporation. The fine-grained entropy is going to 0, just like you would want, and just as we saw it in the page curve.
So can I ask a slightly technical question here? What is the geometry of this island supposed to be? I don't quite understand what your time slices are, or is this, you choose some slice that doesn't hit the singularity and it's some 3-ball inside that, or?
Yes, it's exactly that. Well, if it's spherically symmetric, it's just going to end up being a 3-ball. It's well, it's really only these calculations really only depend on the endpoint. So it doesn't matter on what slice I draw this island. These entropy and area calculations are independent of that. So you can really think of assigning a diamond to this island region, which goes down here like this and then is cut off at the singularity.
Okay.
Are there other questions? Some terminology. So the endpoint of the island, this is called a quantum extremal surface. This was studied earlier by Engelhardt and Wall in the context of ADS-CFT. The exact position of this island is an interesting quantitative test of the ideas that I'll be talking about. It relates to the so-called scrambling time. I'm not going to have time to talk about that, but it's an important check, and it comes out exactly as it was predicted in earlier work. Okay, so our goal in this talk is going to be to derive this formula, but first I want to give it some interpretation, because this formula is not just a formula for the entropy. I think we should really think of this as a statement that's similar to a holographic duality. It's so here's what I mean by that. There's this idea in ADS-CFT called entanglement wedge reconstruction, if you're familiar with it, then that's what I'm talking about. But if not, then I'm about to define it, so don't worry about it. The statement is that the island is in the entanglement wedge of the radiation. So what does that mean? It means that the island is actually encoded in the radiation in a sense, in the sense of holographic duality. Now, it's not holographic, like it's not holographic in the sense of reducing the number of space-time dimensions. You know, if this is if this black hole is d-dimensional, then it's being encoded in the radiation, which is also d-dimensional. But it's holographic in the sense that a region where gravity is important, this black hole region, is being encoded in the quantum state of a region far away where gravity is not important. Well, maybe there are some gravitons, but the strong effects of gravity are not important. It's holographic in that sense. Encoded means that the operators in the island, like say some field operator phi of x that's defined in the island somewhere, can be written as an operator in the radiation in principle. Given the entropy formula that I had on the previous slide, this statement about encoding and holographic duality, this is almost a theorem in quantum information. And that almost theorem is the subject of these many papers. It roughly says that if you can calculate entropies, then you can reconstruct quantum states. And if you can reconstruct quantum states, then you must have access to the operator algebra of some region. However, this is in principle. There are a lot of caveats here, and the decoding map is very complicated and non-local. So I think we should take this picture as a suggestive interpretation in how to think about this. What it sort of says in words is that the island region is, well, it looks like it's far away, but it's secretly not. It's secretly, if we live out here in the radiation, then that island region, we secretly have access to it through the radiation that we've collected. Okay. Now I'm going to go on to the origin of this island formula. Are there any? Let me pause here for questions.
So it sounds like if we could formulate the whole theory just using the exterior of the black hole, because we have all the information about the interior encoded in the exterior.
Let's see. It depends what you mean by theory. So this is not as strong a duality as ADS-CFT. So in ADS-CFT, there are kind of two aspects of it. One is that the quantum state in the bulk is encoded in the quantum state of the boundary. That's a statement that you can make just like about wave functions at fixed time. And that should carry over to a situation like this. But there's a stronger thing in ADS-CFT, which is that the dynamics and the Hamiltonian and time evolution in the bulk so there's a theory in the bulk and there's a theory in the boundary with a Hamiltonian and its own time evolution and everything. And those two things are also equivalent at ADS-CFT. That second stronger version of duality, I don't know of any way of saying that here. So that might not exist here. So it could be a weaker version than what you're used to in ADS-CFT. Other questions? Okay, so let's talk about replica wormholes. The goal is to derive the island formula, which, as I said, was a conjecture. It was motivated by results in ADS-CFT and by wanting to get a unitary answer and by doing this calculation and seeing that it gave something so nice. Now we want to derive this directly from the Euclidean gravitational path integral. We're going to use the replica method. So the replica method is a common trick, and here's how it goes. We're interested in calculating this log minus trace of rho log rho. Logs are hard, so instead of trying to calculate the log, we'll calculate a power. That is, we'll try to calculate this thing, which is called the replica partition function, which is trace of rho r to the n. We do this for integer n. The reason for doing this is because we can, because there's a path integral that does this calculation for us. So we do this for integer n, and then if we could do it for all integers, then under some favorable conditions on the fall-off behavior of this function on the complex n plane, you can do an analytic continuation from the integers to n near 1. If you take n near 1, then this power becomes a log, and so you can extract from analytically continuing this replica partition function, you can extract the entropy from this formula here. So the reason for doing this trick is just because we don't directly know how to do a path integral that calculates this thing. What we directly know how to do is a path integral for this thing. So we're going to use that as a route into the determine the entropy. Before I'm going to draw some Euclidean path integrals in gravity. Before I do that, I just want to sketch the basic idea of how this is going to work. The point is that when you consider replicas, when you do a replica calculation with multiple black holes, you can get new contributions. Okay, so this is a replica calculation. This is supposed to illustrate a replica calculation with 3 copies of the black hole. And when you have 3 copies of the black hole, you can get contributions to the path integral where the geometries join inside the black hole. So what we're going to see is that in the replica method, dynamical wormholes appear connecting the black hole interiors. So this bridge here, this is supposed to illustrate these wormholes. They're actually pretty hard to draw because these are complex saddles. They have complex metric. You can think of them as being similar to instantons. They're complex spacetimes that contribute to the path integral. We can construct them by explicit solution of the equation of motion for gravity together with matter in some certain simple cases, and those cases are enough those will be enough for this calculation that we want to do. So you can construct these replica instantons that join the different replicas when you have an integer number of black holes. Then you have to analytically continue this picture to a non-integer number of black holes. Turns out you can do that as well. And in the replica limit, which is n to 1, these saddles, these wormholes, leave an imprint on certain observables, including the von Neumann entropy. When you take n to 1, the wormholes are gone. So in the actual black hole, there is no, in the actual black hole that you're measuring the Hawking radiation of, there is no wormhole. It's a calculation, think of this as a calculational trick to determine the entropy of the Hawking radiation. So you have to introduce some auxiliary black holes. You find these wormholes, then you take n to 1, the wormholes disappear, but they give you some correction to the von Neumann entropy. Okay, so now I'm going to unpack this slide into 2 or 3 slides with some slightly more detail. Are there any questions first? Okay, so as I said, we want to do this replica calculation, which is the trace of rho sub r to the n. A quick warm up. So remember the path integral calculation of a transition amplitude using the Euclidean path integral. So I wrote an example here that's familiar say from talking about instantons, if you want to calculate the transition amplitude between instanton number n and n+1, then what you do is a path integral on a Euclidean spacetime, where you put a boundary condition n at Euclidean time minus infinity and a boundary condition n+1. These are windings in the context of instantons. Boundary condition n+1 at Euclidean time plus infinity. And this Euclidean path integral calculates for you a matrix element or transition amplitude. Okay, so in gravity, we like to do something similar, but in gravity, we like to calculate traces, because when you calculate traces, that's where black holes show up. So let me first give the standard example of the n=1 replica from the Euclidean path integral. So here it is. What we're calculating here is the trace of rho. It's similar to this instanton like matrix element calculation, but now we're calculating a trace, and instead of a transition amplitude. And when you calculate a trace, that means that you should do this path integral on a circle. So this circle here is the Euclidean time circle. And that corresponds to the fact that we're doing a trace. And then what you're supposed to do is you're supposed to calculate the path integral. Well, we don't really know how to calculate the path integral in quantum gravity, but we do know how to calculate it in the semi-classical approximation. And this is a classic calculation that was done by Gibbons and Hawking. There's a contribution to this path integral on a circle, which is the Euclidean black hole geometry. And that's what this picture is. It's a Euclidean black hole. An important point, and this is different from the field theory calculation, say of instantons, is that in gravity, you don't get to pick the geometry, right? In gravity, the geometry is dynamical. You don't get to pick it. So what do we really mean when we draw these pictures? Well, what we mean is that we pick some asymptotics of the geometry. We pick some asymptotic boundary conditions. In this case, the asymptotics are far away from the black hole. So that's really what we're specifying. And then it's up to gravity to fill that in, to fill in that manifold by solving the equations of motion of gravity coupled to matter. Okay, so the problem that's really been being solved here is we specify some boundary conditions on the asymptotic region, and we want to calculate the path. We want to find semi-classical contributions to the path integral with those boundary conditions. And the equations of motion of gravity tell us, oh, this is the dominant contribution. This is your saddle point that solves those equations. So that's the case of the Euclidean black hole.
So where you only have to work with the classical solutions, you don't have to have quantum fluctuations around those solutions.
Well, for the Euclidean black hole, for the case n=1, which we're doing so far, the answer is that you can include those quantum corrections, but they're small. So for this case, this will just give there will be a gravitational on-shell action, which is 1/g_Newton. And then there'll be a one loop term from the quantum fields, which is g_Newton to the 0, and that'll just be a small correction. But that's going to change in a second. So yeah. Okay. Now we go to the replicas, and I'll look at the case of n=2. And this is where the magic is going to happen. Okay, so say we want to calculate this replica partition function trace of rho sub r squared. Well, there's one obvious contribution to the path integral. Well, first of all, let me say what path integral we're doing. So the path integral that we're doing is a path integral with two asymptotic black holes. Okay, so now the asymptotics here are what I've drawn. It's that asymptotically you have two copies of the black hole, copy 1 and copy 2. There's these i's, j's, and dotted lines. So let me not get into that too much, but that indicates the fact that these two density matrices are multiplied by each other. This is rho sub r times rho sub r. So the correct boundary conditions for this calculation involve gluing together these manifolds along some slits in the manifold. The important thing, though, is just that there's two things that look like the asymptotics of the Euclidean black hole, and then you want to do the path integral, so you ask what the saddles are, and there's one obvious saddle that fills in this boundary condition. The obvious saddle is just two copies of the Euclidean black hole. If we were to just include these two copies of the Euclidean black hole, these are two disconnected copies of the black hole. If we were to just include this in the calculation of the entropy, and then go through the whole analytic continuation and everything, we would get back Hawking's answer for the entropy of the Hawking radiation, and it would be non-unitary, and so I've called this the Hawking saddle. But now that I've set it up this way, it's clear that there's another possibility, which is that you can also get instantons or Euclidean configurations where the black holes are joined in the interior. So these are some higher topology, new potential contributions to the path integral. These are called the replica wormholes, and these saddles do exist. Okay, so this is not obvious. You have to solve the equations. You have to solve the equations of gravity coupled to matter. But you can find saddle points that have this topology, and those are the wormholes. Let's look for a minute at how big these contributions are. So we're doing path integrals, and we have these are semi-classical contributions, so they're exponentials. Hawking's contribution is going to be e to the minus something. This S2 Hawking just is the action of this instanton. Similarly, the wormhole contribution is going to give us another exponential e to the minus S wormhole. But what happens is the following. This first thing, the Hawking contribution, it starts out dominant. At early times, this dominates, but it's suppressed in time. It's suppressed by t. And in particular, you can trace that suppression back to this large entanglement of the radiation with the interior. So when the radiation and the interior become highly entangled, this S2 Hawking becomes large. There are two contributions here. There's the action, and there's a contribution of the quantum fields. It's the contribution of the quantum fields that's making this term suppressed. So this term is getting suppressed in time, whereas this term is small. This topology, having this higher topology, costs you some action. So this term is small but constant, or in fact, growing slowly as a function of time. It's not getting suppressed. Okay, so this term is small but constant. And that's why the wormhole, so this is why the wormholes can eventually take over if your calculations go into the late time regime, which is relevant to the paradox. Okay, so to finish up this calculation, what I've said so far is that these replica wormholes are n-copy solutions with gravitational equation motion sourced by the one-loop matter stress tensor on the replica manifold. You can construct these at finite n in some simple cases. To find the von Neumann entropy, we want to analytically continue to n near 1 and take this derivative. So the entropy is minus z prime of 1. And you could do this calculation too. I'm not going to go through this part, but what happens is the mouth of the wormhole becomes the island. as we take n to 1. And you can calculate the, just from this calculation of the path integral that we discussed, you can take the limit of that as n goes to 1, and extract from that the entropy, and the result is exactly the island formula that was proposed earlier. So by including these replica wormholes in the gravitational path integral, we get back this, this proposal, the island formula, which we already said was consistent with unitary evaporation. It gives a good formula for the Hawking entropy, for the radiation entropy at late times. If we look back at the Page curve, then remember Page said that in a unitary system, in a unitary theory, the true entropy of the Hawking radiation should follow the dotted line. It should go up for a while and then turn over and come back down. And that's exactly what happens when you include the wormholes. So in terms of the wormholes, at early times on this curve, the Hawking saddle is the dominant saddle point in the calculation of the path integral. At late times, the wormhole saddle is the dominant contribution to the path integral. As I emphasized before, the reason that the wormhole saddle can take over is because of this relationship to entanglement, because the Hawking saddle gets suppressed when the fields inside the black hole are highly entangled with the radiation. Okay, I'm going to basically make some observations and concluding remarks, but let me pause here again if there are questions about the replica wormholes.
How do you define the mouth of the wormhole?
Yeah, let me see if I have a.
Or you can answer Marcus's question. We'll do this afterwards, if that's easier.
Well, I can answer this. I'm trying to decide whether I should go. Let me see if I have a slide about this. I might.
We could do it after the talk if it's too technical.
I have a good slide, but I think I don't. I think I didn't. Ah, here it is. Okay. Okay. Well, I think to answer your question, I first have to tell you what it means to have non-integer number of wormholes. And that's what this slide is answering. Because so what I mean by the mouth of the wormhole is, I mean, what's left over when you take n to 1. Okay, because we have n copies of the system. So what's drawn here is 3 copies. And it's important that we assume a Zn symmetry, a cyclic symmetry that rotates the replicas. And in that case, what I was calling the mouth of the wormhole, it's bounded by the fixed points of that rotational symmetry. So it's these dots here. Those are the edge of the wormhole. When you have this symmetry, you can go to a quotient manifold, which is divided by Z3, or Zn. And once you go to the quotient manifold, it makes perfect sense to talk about this quotient manifold at non-integer n. So that's how this calculation is actually done. You first go to the quotient, then you analytically continue in n, and then on what I called the mouth of the wormhole is it's the branch cut where the different copies of the quotient are joined together. That was a little quick. Did that answer your question?
Yeah, thanks.
Okay. Is there another question?
Yeah. It's more a general question. Maybe you're going to comment on this already, but since you, I guess the claim is that that these these replica wormholes, they are accounting, you're saying that they are accounting for the entanglement entropy at late times, they dominate. So my question is there a physical picture associated with this in real time? Is there any way to say what's going on? Hawking's calculation is completely wrong, so what's going on?
That's a great question. Let's see, I am going to sort of comment on this, but let me try to answer that directly. No. So
Next question.
And this is, I mean, this is often a problem with Euclidean calculations, but it's especially true in Euclidean gravity. So the Euclidean gravitational path integral, it gives you answers like for entropies without really telling you where those answers came from, like where the black hole entropy, where the microstates are, for example. And so you could ask, like, so we can calculate the entropy, but we cannot calculate how a given in state evolves to a given out state. That's something that you ought to be able to calculate if you have a theory of quantum gravity. And the Euclidean path integral does not tell us does not give us that information. Presumably it depends on the UV completion. So that's like some microscopic information that we can't access. I think the surprise here is that the entropy itself is somehow coarse-grained enough that it can be captured with the path integral, even though the path integral doesn't know what's happening microscopically.
One more question. Once you start admitting these extra topologies, there are potentially many other topologies that could occur. How well are they under control? Is it known that these wormholes are the dominant contribution at late times? Could there be wormholes with wormholes in them and things like that?
Yes, another good question, which I'm going to sort of get to in the remarks. So including some higher topology opens up a whole big can of worms, you could say. And the answer is that we don't have a systematic understanding of what all those contributions are, or how to sum them up, or which ones contribute to the path integral and which ones don't. If there are just some more saddle points, then that's not going to matter much. That's only going to make, so if there's just some new saddle point that's slightly more dominant, let's say, that's just going to make this even more unitary. I mean, it's just going to make, if it dominates over this, it's going to make the entropy even smaller. So it's not really going to change much as far as the interpretation. There are other potentially worse things that could happen, like the whole expansion could make no sense, or just be completely out of control. And that I'm going to comment on, but I think we don't have a great UV picture for how, we don't have a good UV understanding for how you're supposed to do gravitational path integrals. So I don't think we can fully justify that. I think sort of the best we can do is really to assume that some saddle contributes to the path integral and see if it gives a reasonable answer. But it's not fully satisfactory. Other questions? Okay, so let me make a few comments. Some of them, if not all of them, we've sort of touched on, but here goes. So first of all, does this show that black hole evaporation is unitary? No, it does not, but it, I would say, is evidence in this direction. So why do I say it doesn't really show this? Well, remember what we're calculating. We're calculating the von Neumann entropy minus trace of rho log rho. We use the Euclidean path integral to calculate this without calculating rho sub r itself, or even showing that rho sub r with this entropy exists. In other words, we don't even know in principle how to calculate this rho sub r or how it should be what determines it. We just have this trick for calculating its von Neumann entropy. This is on the same footing as the old-fashioned Euclidean calculation of the black hole entropy, say by Gibbons and Hawking. They calculated the entropy of the black hole many decades ago and found error over 4 from the Euclidean path integral, which we believe gives the right answer, but it doesn't exhibit the microstates. And I think this calculation of the page curve is very much on a similar footing. It gives us what we think is the right answer for the entropy of the radiation. But to really justify calling it an entropy, you might ask for the microstates, and that would be very reasonable. Another comment is, could there be implications for quantum cosmology? So I think we understand black holes, and especially black hole interiors, a little bit better in view of islands. And cosmology has a lot of similarities with black hole interiors. It has horizons, singularities. It has enormous entropies. So does cosmology have islands? Does this tell us anything about cosmology? And the answer to that is maybe. There are cosmological models that have islands. This is something that people are working on now and really trying to understand. But so far, the interpretation of islands in cosmology is unclear. So I just wanted to mention this. But I think, but to some extent, studying black holes and black hole evaporation should hopefully be sort of a warm-up problem for studying cosmology and cosmological singularities. So I hope that people will have something to say about it, but right now it's not so clear. The last comment I want to make that we also hinted at is that wormholes can potentially cause problems. So you could ask, do wormholes violate quantum mechanics themselves? In other situations, wormholes have been discussed. There was a big effort to understand wormholes in the late 80s, early 90s. And it was found that wormholes lead to a lot of problems, and in some cases seem to violate some basic properties of quantum mechanics. The basic reason for that, it has to do with cutting the manifold into pieces. So if you have some manifold with higher topology and you cut it, then in quantum mechanics, we think you should be able to insert a complete set of states. But when you can have these higher topologies and their little baby universes shooting off of your main universe, it kind of changes the rules, and you get what are called factorization paradoxes. So I just wanted to mention this to point out that including wormholes, even if it fixes the problem with the entropy, it raises new questions of how to interpret these wormholes. If you want my take on it, I think this can be overcome. I don't think the factorization paradoxes are really paradoxes. There's something to be understood, but I don't think this is gonna kill it. That's just my view on it. And I think we're at the end, so let me just conclude. The conclusion is that the ordinary rules of the Euclidean path integral can be used to calculate the entropy of Hawking radiation. The result of this calculation agrees with unitarity and quantitatively matches earlier predictions, like the prediction of Page. That's a quantitative matching. These curves, I drew them as straight lines, but they're actually something more complicated, and you can get a good quantitative match with all that. But at the same time, this result also highlights the remaining puzzles of how to interpret the gravitational path integral. It doesn't answer everything. All right, thank you very much.
All right, maybe we can unmute and clap for a very nice talk. All right, other questions?
I have a simple question. Can you comment the rate difference between Euclidean path integral and the Lorentzian path integral, and how do ideal continue from one to each other?
Sure. Yeah. So, well, the way I think about it is that the Lorentzian path integral calculates transition amplitudes from one state to another, whereas the Euclidean path integral prepares quantum states. So let's go back to the instanton. Okay, so if we think about the instanton calculation, if we cut this picture right in the middle, then we get a spatial slice, and there's a quantum state on that spatial slice, which we can think of as being the quantum state prepared by the path integral on the half space.
Okay.
So the way I think of this picture is that the bottom half of the picture prepares the quantum state n. The top half of the picture prepares the bra. And so the full path integral calculates this overlap. The Lorentzian path integral also calculates transition amplitudes, but then you have to input into the Lorentzian path integral what state you want to use. Okay, so
Okay.
so like these, like when I was saying that we get the page curve, I was sweeping something under the rug, which is really we need both Euclidean and Lorentzian evolution to derive that. So we use Euclidean evolution to prepare the initial state, and then we use Lorentzian evolution to allow the black hole to evaporate. And then there's a ket. So the calculations that we're really doing are like Schwinger-Keldysh calculations, where there's a preparation of the state, and then there's a Lorentzian piece of the contour, and then there's a ket.
Okay. I think I got it. So another question is, the theta line application in the Coleman solution is cosmology constant?
Not that I know of.
Okay.
Not that I know of. So there's a big difference between the wormholes that we're talking about now and the wormholes that we're talking about then. And the difference is the size. So in the Coleman story, they had Planck-sized wormholes, which they could then integrate out and get a local, sorry, not local, a non-local effective theory from integrating out those Planck-sized wormholes.
Okay.
In the current story, the wormholes are as big as the black hole. And that's why they're under control. So the old story was never really under control in the gravitational path integral, because the wormholes weren't really stabilized by anything, or they weren't solutions. They were off-shell configurations that people were sort of hoping would contribute to the path integral. The new wormholes are saddle points, which are weakly curved and under control and black hole sized.
Okay, thank you.
Can I ask a question? It's a kind of maybe in a way following up on Da's first question. So something I totally don't understand. You know, when the page curve turns around, that is absolutely back reaction is very important there, right? The Hawking radiation is carried away a fraction of order 1 fraction of the black hole mass. And I never heard you say the word back reaction. So somehow these saddles, are they really calculated in some back reacted geometry, or what is going on?
Yes, they're back reacted. So they're saddles. So first of all, let me say what equations they're solutions of. So these are, if you write the Einstein equations with the expectation value of the one loop stress tensor on the right-hand side. So G mu nu is the expectation value of the matter T mu nu one loop on the right-hand side. They're solutions of those equations, which include back reaction, because when you go to late times, that one loop contribution is the Hawking radiation, and it's large.
So okay, good. So all right. So you've got, but in a way, you know, that sounds to me like and maybe this is like, maybe, I'm sorry, maybe I'm asking my same question, my first question again. But so that sort of sounds like you're taking into account some classical back reaction on the geometry. But then you're saying, somehow it seems like you're saying these wormholes then know about the quantum information aspects of this.
Yeah, that's right. The reason they know about the quantum information aspect is basically because this picture here this is not obvious, but this picture here, if you ignore the geometry part, just calculate the one loop matter path integral on this geometry here. That turns out to be almost identical to the calculation of the entanglement entropy of the quantum fields inside the black hole with the quantum fields in the Hawking radiation. The entanglement entropy of the joint region. Yeah, that's a little hard to explain from these pictures. Let's see. Maybe I can.
Okay, you know what? Let's get some more questions. If you're able to stick around a little bit afterwards, we can have some more formal discussions.
Yeah.
I don't. So let's give other people a chance, and also if people don't want to stay too long.
Sure. Yeah, I'll just give the one sentence answer, which is that fact is hiding in the one loop terms that do contribute to this to these calculations.
Okay. All right. Other questions? Okay. Well, let's go ahead and thank Tom, and hopefully he can stick around, and you're welcome to stick around as well for additional discussion. Thanks very much, Tom. Yeah, I didn't understand.